All right. So hi, everyone. It's good to see everyone. In this presentation, we're going to discuss the National Wildlife Federation's role in coastal resilience to start off, just to give a little context and background on why I'm working with scientists at the University of Maryland Center for Environmental Science, Horn Point Laboratory. Then I'm going to turn the presentation over to Jeff Cornwell, who will talk about his research on the water quality benefits of oysters in the Chesapeake Bay. And make sure you stay till the end, because I'm going to wrap it up with presenting an innovative concept that we're working on to green gray infrastructure. And we'd love to hear your input and questions on that. And, you know, questions, we'll have plenty of time for questions at the end for anybody who has questions. So to start off, basically, the National Wildlife Federation has this goal. Let me make sure this is looking properly. There we go. So our goal for the coasts is to protect and restore coastal ecosystems. And one of the ways we do this is to sustain fisheries and wildlife. That's the reason. And to protect people and wildlife from rising sea levels and intensifying coastal storms. Let's see, having a little bit of screen difficulties. I actually am in Florida today. I'm helping my grandfather out in Florida. So I just set up a new office space. So let me make sure this is gonna keep flipping.
No worries.
There we go. Okay. So my shared screens are somewhat working. So our strategies for achieving this are to accelerate restoration of large-scale coastal ecosystems, to expand the use of nature-based features, such as oysters on oyster castles, which I'll talk about, and reef balls, and to reform flood insurance and disaster preparedness programs. To advance the protection of nearshore marine ecosystems is another strategy in this goal. And our desired outcomes for national infrastructure are to advance and communicate the scientific case for this. Which is why we're working with scientists and helping to support their research at the University of Maryland. Along with other outcomes for large-scale ecosystem restoration and nearshore wildlife that are described on this slide. Some of the key activities that we're working with, or we're working on to meet these goals, is to develop guidance for conservation practitioners, to work to reform federal policy, and engage in ecosystem restoration. We're engaging in restoration in the Gulf of Mexico, the Everglades, and the Mississippi River Delta. Those are some of our large-scale projects. And we're also doing a bit of work in the Chesapeake Bay, which I'll go over. And our priority projects are nature-based approaches that showcase technical innovation with the opportunity to replicate this at scale. So one of our recently released reports is called Softening Our Shorelines. This is a policy analysis of living shoreline practices throughout the Atlantic and Gulf coasts. And basically we conducted an inventory of all state policies and regulations that inform living shoreline implementation. We are also working on a service provider training program to help service providers get really comfortable with some new and innovative approaches in living shorelines, as well as the basic approaches to implementing living shorelines, so we can increase their installation and provide more of that really critical intertidal habitat for our wildlife. The report is available at this link, www.nwf.org/softening our shorelines. So one of our most recent projects in the Chesapeake Bay was the Conquest Beach Living Shoreline. This occurred before I started, but I'm so excited to get out there and see it. This is kind of an innovative innovative approach, we worked with the Maryland Department of Natural Resources in Queen Anne's County to construct it. And it was the first shingle beach shoreline in the United States. So we're really testing something new that we aren't aware of being implemented in another place. We incorporated climate resiliency into the design proactively so that the shoreline could keep pace with sea level rise. And we also incorporated some small dunes here. You can see the before photo. It's funny with projects, you always get so many great after photos and you get a few before photos. But this shoreline was really eroding, and it was eroding right up into the town. So we were to help this town develop an approach. And the reason that NWF got involved is because we really want to help test out and promote new approaches to natural infrastructure. Another project that we're currently working on is in the town of Oxford. And this is just a little snippet of a design that we're working on with the town. And we're working to design resiliency features such as these offshore dynamic living islands that will provide wildlife habitat while also protecting the infrastructure behind it. You can see the road right behind this design, East Strand Road, is essentially right up to the water's edge, and it's getting consistently flooded. It's one of the only roads for folks to get to their houses on the peninsula towards the right side of this photo. So yeah, we're working with the town of Oxford on multiple different approaches throughout the town. So this is just a little snapshot to give you a preview. So our resiliency work, I'm really excited to be working with the National Wildlife Federation on this. I'm really passionate about this type of restoration work and providing more spaces for wildlife to thrive, but also people to thrive with rising sea levels and climate change. The Chesapeake Bay region particularly is going to be hit pretty hard. So providing these approaches that, you know, improve wildlife habitat while also improving human habitat where people live will be really key. So we're excited to be working with these towns on innovative concepts. So I'm going to turn it over to Jeff. He's going to talk more about his research on oysters in the Chesapeake Bay. And then we'll turn it back to me for that innovative concept I was talking about at the beginning. Let's see.
Okay. So I'm going to start sharing my screen. Okay, here we are. And let me go to the full mode. Okay, so I've got a little inset where I see everybody. Very good. I'm Jeff Cornwell. I work on a variety of water quality issues in the Chesapeake and in other systems. And over the last couple of decades, I've gotten involved in trying to develop an understanding of how oysters affect water quality in coastal systems. In this project I'm working with that I've described in terms of some of the shoreline work is with Matt Gray and William Narden. Mike Owens has been doing this work in my laboratory for a very long time, and really got going in terms of a lot of the data I'm going to show was also in conjunction with Lisa Kellogg at the Virginia Institute of Marine Science. And the funding for all this has come from just an incredibly broad variety of different sources, including the National Science Foundation, NOAA, as well as the Palmer Foundation and others. And so water quality, I think this is sort of preaching to the converted, but I'll just say a few things very quickly. That nitrogen and phosphorus are essential elements in terms of all photosynthetic processes, but it's leakage into waterways that greatly increases the nutrients in aquatic systems. And it really becomes the #1 concern at the Bay program level in terms of issues with inputs from our watershed. The consequences of nutrient enrichment include the loss of water clarity and subsequent loss of submerged aquatic vegetation, extensive seasonal anoxia in the main stem of the Chesapeake Bay, with stratification, with fresh water on top and saline water below. You get a depletion of oxygen starting between 20 and 30 foot below the surface of the water. And it goes beyond actually just losing all the oxygen. You accumulate hydrogen sulfide in the bottom water as well. We also get blooms of harmful algae, and then loss of habitat because of the anoxia and other issues with for sessile and motile animals. So what I want to do in this part of the presentation, show how oyster removal of nitrogen and phosphorus fits into the management context and talk about the best management process. Chris Moore, who is on this call at the Chesapeake Bay Foundation, is one of the members of our panel on this. And it's really, what I'm doing is presenting a lot of the work that a team has pulled together on this. I'm going to use the work we've done at Harris Creek as an example. And I'll describe that in a little bit more detail down the line. And to distinguish the work that's coming up in the future is talk about engineered structures, reef balls, oyster castles, versus the kinds of large-scale restoration with on-bottom planting of oysters. Some definitions: denitrification. It's the removal of fixed nitrogen to produce N2 gas. It's a microbial process and occurs everywhere from wastewater plants to sediments to oyster reefs to wetlands and beyond, including in groundwater and farm fields. Best management practice, EPA approved practice, and is credited towards meeting water quality goals. An example of this would be cover crops. If you travel out here on Delmarva or all over the watershed, you'll see signs indicating that cover crops have been planted to ameliorate some of the excess inputs of nitrogen and phosphorus into the Chesapeake. And then total maximum daily load, which is, it's a modeled amount of nitrogen and phosphorus input that provides an acceptable amount of acceptable water quality in a given part of the Chesapeake Bay. And it's sort of the goal that we're trying to get to in this system. How much nitrogen and phosphorus do we need to remove to meet these water quality goals? The other part of this is that, oysters are largely depleted in this system. These are wild oyster harvests from 1870 to last year. And what you see is that, and this is a pretty broad proxy for biomass. There are other approaches that have been used, but just looking at the landings of oysters, they've plummeted for a variety of reasons, including, this was sort of, a lot of harvest that was occurring in shallow waters. It doesn't occur anymore. Sort of ups and downs over time, but when diseases started kicking in here in this part of the system, it pushed it over the edge, combined with, very strong harvest pressure that degraded the quality of the reefs to where now we're at a tiny fraction of the historic harvest within this ecosystem. So this is kind of my viewpoint of the process, in that, and I started out in thinking about these things in wetlands, where initial publications on the Chesapeake Bay said things like nitrogen and phosphorus are removed in tidal wetlands. And when I went to look for data, I couldn't find any, and spent a lot of time working on developing some of the numbers for that. And it's the same thing here. We know oysters are great for the environment. They filter a lot of water. And in theory, they take out a lot of nitrogen and phosphorus. But looking at the relevant data, there wasn't a lot. We started developing some a little bit over a decade to a decade and a half ago, where we're looking at the production of N2, denitrification in general, and cores near reefs. That doesn't tell you the whole story. When we do whole community incubations, take the oysters to go with the sediments and everything on the bottom, we see really very large nitrogen fluxes out of the sediments, which is a water quality benefit because we're taking it away from the ability to regrow algae. And finally, there's another part of this. I'm not going to emphasize this much, but when you remove nitrogen and phosphorus to tissue, we've credited already aquaculture. When they remove nitrogen and phosphorus, the tissue part of the oyster, it can be credited and be considered a benefit to the Chesapeake Bay. We're looking at with a new BMP, and hopefully things will move pretty quickly forward on that, looking at sort of the buildup of biomass in reefs as another creditable removal of nitrogen and phosphorus. So from a policy perspective, there were questions, was this significant enough to warrant management use of development of a best management practice? And the Bay program asked a number of us to get involved, and the answer is yes. The Bay program's perspective is that we're looking for all opportunities everywhere to remove nitrogen and phosphorus. It's big and small. As we've really removed nitrogen and phosphorus with the most cost-efficient ways to remove them, upgrades in wastewater, some of the farming practices. Now to start getting to our TMDL targets, we're looking much more broadly. And so again, we've already gotten to the point where aquaculture crediting of nitrogen and removal by a tissue is an approved practice. Can we credit denitrification and the buildup in biomass in non-harvested areas? So this has been going on a very long time, and our panel, we hope, and I think Chris Moore will hope that we're going to wrap this up sooner than later, but we've spent a lot of time as a panel looking at all the different kinds of deployment of oysters that occur in an active sense, and considering the water quality benefits them in terms of nitrogen and phosphorus. There are some things that, like, the improved water clarity is hard to quantify, so that's not part of this. Removing sediment through filtration is fine, but that sediment's ultimate fate was going to the bottom anyhow. So we're looking at things that are really a net to the ecosystem in terms of nitrogen and phosphorus removal because of oysters. So this is how a biogeochemist or a geochemist thinks about the world. Things move in, and so basically there's a lot of microbiology and chemistry and all this, but in the end, we're accountants. And so looking at Harris Creek, there are inputs of nitrogen and phosphorus from the watershed. In that system, a big part of the nitrogen and phosphorus inputs are actually washing in with the tides from the main stem of the Chesapeake Bay ultimately. You also have atmospheric inputs. This is all processed in here. We get assimilation, we get filtration into oysters. They're prolific at removing particles. And some of that's incorporated into biomass, some of it gets buried, and some of it just gets remineralized and changed and pushed back out to the Chesapeake main stem. But it's this couple of processes here, the denitrification within the oysters, the incorporating tissues, and possibly increased inputs in the sediments, though that's a little bit harder to determine. And so I'm going to focus a fair bit on denitrification, which is probably the dominant water quality value of intact oyster reefs, but not the only one. So thinking about this, it's not a matter of measuring denitrification. It's a matter of measuring the enhanced amount of denitrification. And so our process has been to provide defensible, verifiable estimates of nitrogen reduction from enhanced denitrification. And it's a matter of going from the idea that, yes, there's denitrification going on to coming up with hard numbers that managers can use in the Bay model and other places. So going to Harris Creek, 350 acres of spat on shell have been planted with juvenile oysters. The substrate, the bottom has been modified by adding shell in some cases, but also adding larger chunks of granite and other kinds of ways to build up to keep these oysters really off from sinking down into mud and or getting buried. A considerable cost has been put into that. And so the question is, what are the water quality among other benefits? So for perspective, 350 acres is about the size of the National Mall. What you see below that depiction is what we like to see in an oyster reef, 3 dimensions. The harvest reefs typically are very flattened because of the harvest practices. And in fact, it's this that really, you know, if this can keep building up with time, it can outlast the sedimentation and not get buried. The way we measure these things are in enclosed chambers, and we bring essentially a part of the ecosystem into the laboratory. This is what it looks like after the end of an experiment. But divers deploy these trays, leave them out for a month. We bring them back, sealed with water on top, and do incubations and do time courses of change of the chemistry of the water above this. And by that, what we end up with is a number that's a rate of nitrogen or phosphorus exchange or removal on an aerial basis. So the numbers I get are things like micromoles per square meter per hour, but you can make kilograms per hectare per year out of this, which would be the ultimate goal. And I'm not going to show a lot of data, but looking at Harris Creek, for instance, looking at numbers that are pounds per acre per day, you know, depending on how much biomass there is in the where we do the assessment, we get very, very high rates of actual uptake of production of N2 gas. It's a big enhancement over what you see for the sediment in the other parts of the system. Right now, we're looking at using parsing out biomass and extrapolating to the system using biomass. So biomass of oysters, dry weight biomass of the tissue, is going to be critical information to know to do our extrapolations. I'm not going to explain this much, with the exception to say that if you just look at the sediments in a reef, you don't get much of the denitrification. You really need to be considering the whole community. Without the community in there, you end up with a very biased and low estimate of denitrification. If we could just do cores, life would be very easy. They're easy to bring in and handle. When we do the whole incubation with the community, we're looking at many man days per net flux number that we get in terms of getting the numbers out of that. So this is from some of the BMP stuff we're working on. But, you know, there's a flow chart. Are there acceptable denitrification assessment techniques? Does include the whole reef, et cetera, et cetera. But the bottom line is this: we don't have enough data in this world to take one number and extrapolate it to all reefs in the Chesapeake Bay. And it's possible that we may be able to parse that out over time, but the way that we're looking at this is that there probably has to, especially with large scale restoration, you need to do an assessment to get those numbers. Until we have a body of information that suggests that we can have some default numbers. And this is what always has come up in all of these considerations: is what's the number, what do oysters do? And the answer, unfortunately, is where are you? How old are they? There's a lot of things that go into it. And so for the time being, measurements need to be done before we do crediting, presuming that the BMP is accepted. Now, the implementation of this best management practice and what we're considering, and this is, of course, it will go out for public review, hopefully within the next 2 or 3 weeks or less. But measurements, we need to measure the biomass, the denitrification rates. They need to be done seasonally if you want to extrapolate this to different seasons. And we need to report all these things of location, physical parameters, biomass, and the rates. what the managers will do at that point in time, because the BMP process is not something like nutrient trading. There's no money attached to this. We're just, as a scientific panel, determining whether or not there is a scientific rationale for crediting nitrogen and phosphorus removal. Other things can happen, like with the aquaculture part of this. There can be crediting, potentially nutrient trading, but that's not part of what we do. So they will develop an implementation plan. How do you report this to EPA? How much nitrogen and phosphorus is there based on measurement? So that's kind of the on-bottom component of this. What we're talking about with this project that we're just starting is engineered structures. And so I'm going to talk a little bit to start on some things we're doing with reef balls. And the reef balls are like this. Chesapeake Bay Foundation builds a lot of these. They've been deployed by lots of different NGOs. When you set them with oysters, we've brought up a few that look like this. It looks like a blooming onion at a restaurant. There's so many oysters, and it's three-dimensional, and there's as many on the inside as there are on the outside. So there's a lot of oysters here. And so we did work in 2018 and 19 in various places between the Chesapeake River bridges. For those of you who are familiar with Route 50 coming into Cambridge, Maryland, there's about 400 of these deployed. Out at the mouth of the Chesapeake in 2 different places, there's over 1,000. So there's a lot of these things out there. Each has an surface area of about 2.5 square meters. And this is an example. There's some side scan sonar, and you see lots of these things deployed out here in the mouth of the Chesapeake River, and spread out over a number of acres. Their primary goal of deployment is not water quality, but habitat for fish and other species. But they also serve a water quality component as an added bonus. And so we take these things, incubate them in large scales. They're brought up, put in water without having any bubbles, and it's quite an involved process. And we do time course incubations, and we come up with how much nitrogen, dinitrogen is produced per reef ball. Now, oyster castles are the focus of our current work. And where we're working right now is at the Horn Point Laboratory here on the eastern shore. And we have eroding areas throughout this, what we call Lakes Cove. And we have a large environmental education facility here. Over the year, tens of thousands of K through 12 students have come through on this. And my colleagues, led by Matt Gray, have deployed a lot of these little, they look like cement blocks. Many of them have been set with oyster spat. And the idea is to slow down this process you see in the lower part here, where we're getting just massive amounts of loss of shoreline. And so we got started. The project is we just have what I would consider preliminary data, but the data is very interesting to start. And so these are what these castle components look like when we bring them into our chambers to incubate them. We circulate the water with a pump, a submersible pump here, and that keeps it homogenized. The incubation tank is the same that we've used for reef balls. If we consider what happens in that tank, and this is to show you an example. So what's happening is the respiration of the animals and the microbes are pulling out the oxygen over time. So here's time of day, in terms of hours. Here, dissolved oxygen is going from near saturation up here to pretty depleted over the course of a handful of hours. What happens while that's going on is dinitrogen gas, which of course is very high in concentration because the atmosphere is largely dinitrogen, and we see an increase. How can you see this 5% increase, or rather 1% increase over time? Is that we use gas ratios. Mass spectrometers can tell us the ratio of this species to argon to 1 in 10,000 parts. So each of these numbers is good to a fairly high level of precision. So we're able to use this to get a precise change in the dinitrogen concentration. And actually, these are some of the ones that we pulled in. This was at an extremely low tide prior to us making the measurements. Let me go, go back. So if we extrapolate these numbers, and this is a gigantic extrapolation based on too little data, and in sort of in a fall season when we think the numbers are probably a bit low, but you know, each of these blocks removes about 0.013 pounds of nitrogen per year. If you were to do that extrapolation, it could be considerably higher depending on if you get the full seasonal coverage, which was our plan. Using a conservative estimate of $40 a pound, that number comes from what the state was using in the Conowingo Dam debate in terms of the value of nitrogen coming into the bay. It's cost of removal. Some of my colleagues think that's a very, very low number, but each of those blocks in a year is worth about half a buck of nitrogen removal. And of course, the real question here is it's also adding to the value of shoreline protection. So, you know, you're looking at 1,000 of these blocks valued at greater than $500 per year when you get the oysters to 2 inches in size. And it'll be interesting to see, following these out over time, to develop an understanding of how much added value comes as the oysters happen. And we're not talking just oysters, there's a whole community there of other filtering organisms that attach to this. And so when we get back into the field again, which we're hopeful is sooner than later, we'll be making lots more assessments in Lakes Cove on these. We're looking to extend this work beyond Lakes Cove. And, you know, when you have a new technique and approach, like taking these large structures and incubating them, a priority is to publish the initial work, to get peer review on it and ensure that those things are really helpful when you want to start using these things in a management context. And so the final thing I'm putting up here is a cartoon from the Washington Post from some initial work we did with Lisa Kellogg. Nitrogen filtering oysters being extremely valuable to the Chesapeake Bay. And the thing I'd like to emphasize in the end is that, you know, you're not, with shoreline work or reef balls, you're not covering that much of the bottom with them. And so extrapolating this out, it seems like a relatively small amount of nitrogen, but my colleagues at the EPA are looking for every microgram of removal they can find in as many places as possible. And so we're trying to, in the end, just provide the quantitation of how much nitrogen phosphorus is removed. That'll get incorporated into Chesapeake Bay models and into the team and go towards reaching team DLs. And so all removal is good. And this has the added benefit of, in some cases, of habitat, shoreline protection, and all these other features that are there. So I'll stop there.
So I think I'm going to try to share my screen again to tell you guys a little bit about an innovative concept that we're working with CEs to develop. Let's see. All right. Let me make this a little bigger. Can you guys see my presentation?
Yep.
Perfect. So Jeff talked a little bit about the oyster castles that were installed in Lakes Cove. So some of the scientists are working to do modeling studies of these castles to determine whether planting oysters in situ, you can see in the middle photo, they're planting oysters right in the system onto those oyster castles. And some of them have oysters, some of them don't. So this got us thinking, how can we get more oysters planted in more places in a really beneficial way? So we're working to develop a concept that's shown on this next slide, to plant oysters on offshore breakwaters. So we're working to include potentially oyster castles, planting the oysters in situ, and do some design and modeling work on 2 locations. And we're applying for funding to do this. So we're really excited about this potential concept. We'd love to hear what you guys think of it with your questions or comments. And really special thanks goes to the Palmer Foundation for funding this work. They funded a portion of the research in Lakes Cove, and we're really just happy for their support. So if you guys have any questions, we're here for questions.
Great. Thank you so much, Amanda and Jeff. And we actually just had one come in from Matt Pluta from Shore Rivers. Jeff, thank you for the presentation. Very informative. To your last point about counting any and all nutrient removal from oysters, regardless of size, understanding that oyster gardening programs are small compared to the grand scheme of restoration efforts. But has the BMP work group assessed the removal from participating oyster gardening programs? I'm thinking that information can be a good tool for outreach and engagement with the public. And Matt, you're obviously on, so if there's anything else you want to add, you can also just say it.
Well, we actually I haven't thought about that, you know, with essentially, you know, people hanging oysters off of their docks and whatnot. That's probably quantifiable. A lot of those are being used to for deployment elsewhere, though. And I think, you know, in that where they're being put is probably where that would happen. But going back to your other point in terms of sort of the whole thing, I've been on a bus tour with you, Matt, looking at you know, basically people putting in small mini wetlands in various places in their yards and trying to intercept things. And I think it's the same thing there, you know, that kind of removal, you know, in small scale, you know, a given place might not accomplish a lot, but if you had 1,000 of these, you know, throughout the city of Cambridge or other places, obviously that's when you get to something that, you know, really can make a difference in say Choptank River water quality.
Anyone else have any questions? Feel free to use the chat, or you can just unmute yourself.
This is Peter Marks. I've got a question. I was doing something different last week. I was on a Zoom briefing call, another one. But the issue was about federal relief for oyster aquaculture, because so many of them, basically their market has been restaurants and their market is gone. And they have all these oysters growing and they have no way to get rid of them. They have no income coming in. There was some discussion about possibly using these mature oysters as live oysters on reefs. Has there been any discussion by you guys? Is that something that is doable and helpful? Is this like all of a sudden a great resource that didn't appear to be around before? Or anyway, just wanted to hear what folks thought about that.
Yeah, I hadn't really thought about that. I was aware about the marketing issues pretty much, but that would be an innovative use for them. You know, if they could derive, you know, at least sort of stem the bleeding in terms of the finances, and this could be adapted to that. I mean, putting out reproductive oysters into any of these environments could potentially be a benefit. Yeah, I don't know when a a lot depends on when these remarkets will reestablish.
They had both diploid and triploid oysters too.
Right. Yeah. And of course, the triploids aren't going to help you a lot, but you know, one of our local growers here in the chop tank, you know, they had a number of theirs grow to 4 and 5 inch size, and actually, there turns out to be a market for some of those later on. But when you're growing them in floats, you know, you really run out of space pretty fast.
Thank you.
Other questions? Last chance. All right. Well, hearing none, thank you all so much, Amanda and Jeff, for this amazing presentation. Looking forward to seeing some of that innovative work, Amanda, in the future, and hopefully have you back to kind of talk about what that looks like.
Yeah, absolutely. I look forward to it.
Great. And like I said, this has been recorded, so we will have a link that we can send out to folks afterwards and anyone that missed it. But yeah, I appreciate Jeff, Amanda coming on and talking a little bit about your work, and I hope everyone else has a great rest of your day.
Thank you, Kristen. Bye.
Bye, everyone.
Thanks, Amanda.
Thanks, Amanda and Jeff.